Hello everyone. So today we are going to discuss banking of roads from the chapter circular motion. So before actually moving to the topic banking, let us discuss this situation which is presented over here. So here we are given a horizontal rough circular track on which a car of mass m is moving with a constant velocity v. The radius of this track is given as r, and this view which is presented to us is the top view of the situation. Now what we need to find is the Vmax of the car at which it can take a turn without skidding. Now to find the Vmax, first of all let us draw the free body diagram of this situation. So if I draw the free body diagram, this is the car. So this was the top view of the situation. Now while drawing the free body diagram, I have considered the back view of the situation. What will be the forces acting on the body? Come on, let us see. First force will be the normal force that will act normal to the surface. Next force will be the weight of the car which will act perpendicular to the car. We know that this is along the center. The centripetal acceleration is v square by r. This we know. Now, what will be the third force? Obviously, it will be the friction force. But the question is, where the friction will act and what kind of friction will it be? Now, in this case, when a car is going to take a turn on this horizontal circular track, as soon as the wheel of the car is going to touch the surface of the road, the point which will come in contact with the road surface will immediately come to rest. Hence, there will be no slipping in this condition. And what kind of friction acts in no slipping condition? It is the static friction. And static friction quality, we know that it will act that much, how much it is needed, and in the direction where it is needed. Now here, since the acceleration is along the center, thus the friction, static friction will also act along the center. So here the friction will be acting in this direction on the wheels. Now just we have to analyze the forces and we will get the Vmax for this situation. So writing the first equation, vertical force balance, that will be N is equal to mg. If we write the force equation in the along the center, then this friction force is equal to mass into centripetal acceleration of the car. Now what we need to find? Vmax. If I have to maximize the velocity here, can you change mass? Can you change the radius of the track? No. What will change? The Fr will change. So to make this Vmax, I will make this Fr also maximum. So this we can write like this also, that Fr max is equal to m into Vmax square by r. Now what is the maximum value of static friction? It is coefficient of friction multiplied by the normal force, and we can write from here m Vmax square divided by r. Now it is just mathematics. Substitute n is equal to mg, m Vmax square divided by r. M will cancel out. From here I get Vmax is equal to mu g r square root. So this is the expression which we have got for the maximum velocity at which the car will take a safe turn on this particular horizontal rough circular track. Why I am always emphasizing this rough circular track? Because my next question is going to be based on that one only. Now suppose I remove friction from this road. Now in this case there is no mu. Now the road has been made smooth. Do you think that this car can now take a turn on this road safely? No, I don't think so. Because the m will now also cancel the mg. But will there be any force which will provide the centripetal acceleration? No, because that was the friction force only which was providing this centripetal acceleration. But now in this case the road has been made smooth. So we can note down here that on a smooth horizontal circular track, we cannot take a safe turn. But if we make this surface rough, we get the maximum velocity, that is mu gr. That means if you maintain your car velocity equal to this or less than this, then you can take a safe turn. Else what will happen? Let us analyze that situation also. If you increase your Vmax above this, then if we increase this V, what will increase on the right hand side? Can you increase mu? Can you increase G? No. So R will increase. So as you increase the V, R will increase. What it means that if you take the turn higher than that speed, then this car will take a longer radius, and if that radius is more than the road radius, then you will go and hit this road, then the case of accident will happen. That's why it is said that this should be the maximum velocity at which you can take the safe turn on this road. Now you can note down all these things, then we will move to the concept of banking. Okay, so now let us discuss the concept banking, from which I have introduced the lecture. Now, as in the previous situation, I have shown that when the road was smooth, we were not able to take the safe turn on that particular road. Now, what if I bank the road to an angle theta? What the word banking means is that we are making this road tilted to an angle of theta from the horizontal. Now, let us see what is going to happen in this situation. Here again, this road is smooth. Now, if you are not able to visualize this situation here, I have made it here also. Like, this is the back view of the road from where the back of the car is being seen. Okay, this is the road which is inclined to an angle theta, and from back, if you see, you will find this road going like that. You have seen this concept banking used in the death well also. If you have seen a death well where a person inside that well rides a car or a bike on that particular thing, their shape is conical, that is, the radius keeps on increasing. Why it keeps on increasing, we will see further in this lecture. Okay, so first of all, let us analyze the forces in this situation, that what extra thing we are getting while we are going to bank the road. Okay, so where the normal force will act, it will act normal to the surface. Where the mg will act, perpendicular to this part. Okay, now let us break down the components. This will be my horizontal axis, this will be the vertical axis. If this angle is theta, then this angle will also be theta. Mathematics, this is theta. If you extend this, this is 90, this is 90 minus theta. Okay, then this will be again theta, then vertically opposite angle, this is also theta. Okay, now let us break down the components and write the equation. This will be here, this will be the center along which it is performing the circular motion, and it will have the centripetal acceleration similar to the previous case. This is similar to the previous case as it was in the horizontal rough circular track. So now this n vertical component is n cos theta, that will be equal to mg. What is the horizontal component? N sin theta, that will be equal to mv square by r. What have we noticed here? What different thing have you noticed here in this banked situation? Earlier, when the road was smooth, this normal had cancelled the mg, and hence you are not able to take the safe turn. But here, in this case, there are two components of normal. See, earlier the car was horizontal, this normal has cancelled the mg. But as I shifted this car towards inclined track, this normal has given two components, a horizontal component and a vertical component. Now this vertical component will cancel mg, but this extra horizontal component is going to provide the centripetal acceleration. So this is the edge of banking the road, that why we have introduced the concept of banking. This should be very clear. Okay, now we can find the speed, that what is the safe speed, so that we can perform a circular motion. Just divide these two equations. If we divide the equation number 2 by the first equation, this is the second equation, this is the first equation. If you divide this, then you will get tan theta is equal to v square divided by rg, and from here what do I get the value of v? That is under root of rg tan theta. So this is the particular safe speed on which we are going to perform the safe circular motion in this track. And now let us analyze this V also. Last time we have also analyzed. If you increase V, can you increase G here? G is what? Acceleration due to gravity. It will not increase. Can you increase theta? This banked angle, it is fixed. Tan theta also constant. So again, if you increase the V, R will increase. That is, what do I mean by this? You can see here. Let us suppose that this was the situation. Okay, let us make it more slanting. Let us suppose that this was the situation. You are here performing a circular motion at a speed V. Now you have increased the speed, R will increase. That is, you will perform a new radius which is greater than the previous radius the circular motion performed. This concept now can be compared with the depth well. As soon as that rider increases his speed, it tends to move up the well. You must have noticed that. And as soon as he decreases his speed, he tends to go lower than that. So this was the V here for the smooth case. Now, what will be the situations when our car will have a speed greater than V and less than V in case of a rough bank surface? That we are going to see further in this lecture.
Go.
So now let us discuss rough banked surface situation. Earlier that banked surface was smooth. Now today friction will play its role. Now again let us analyze the forces first of all. Where the normal will act? Always perpendicular to the surface. Mg will act. Where Mg will act? This will act downwards. Now friction. Friction always depends on where it will act, okay? The direction. Now how we will judge the direction? We will make two cases here. First I am going to discuss this case that when you drive the car greater than R, G, tan, theta. Okay? This is the first case. We have derived this R, G, tan, theta earlier for the smooth bank surface. We will discuss two situations. When the speed of the car is more than that, another we will see less than that. So now, if the speed was more than that, I have already discussed that at that particular speed, the R will tend to increase. That is, you will move up in the circle. You will move up in the circle. Now, if you move up in the circle, the friction was always the static friction, as I always told in the start of the lecture. Now, if you try to move up the surface, the friction whose tendency is to act against the direction of motion, it will act downwards. So here the friction will be acting in the downward direction. This is the direction of friction. Why? Because the car will tend to move upward. Okay, is this clear? If this is clear, then it is all mathematics. The physics is that when you drive the car at a speed greater than R, G, tan, theta, then the friction is going to act downward because the tendency of car is to go upward, because as you increase V, R will increase. So now just to draw the FBD and write the equation, we will get the value of velocity. So let me draw this separately, neatly, so that you can visualize the forces more clearly. See, this was the plane. Okay, this is the normal force. This is the mg force, and this is the friction force. Okay, now our axis, this is the horizontal axis, this is the vertical axis. This angle was theta. So alternate angle, this will also be theta. Previous situation we have seen that this angle is also theta. Now simple mathematics, trigonometry. Let us break down the force into components. This is n cos theta. N cos theta will be equal to what? Mg. Here not only mg, the friction will also have its component, that is Fr sin theta. This is Fr cos theta, this is Fr sin theta. Hope you know this. This is Fr sin theta. This is the force balance in the vertical direction. Now horizontally, that force will be equal to mass into acceleration, Newton's second law. Okay, what are the horizontal forces? That is n sin theta plus Fr cos theta, that will be equal to mass into centripetal acceleration. Now physics is over. It is now pure maths. Now let us solve this equation and find the velocity of v. Basically, here I have to find the v max. Okay? We have to find v max. We have to find the v max at which the car can reach the highest point of this banked track. Now, again the same question. For v max, Fr will be maximum. How it is maximum? See, as you go up, the friction will also increase, because as you go up, the tendency of car going up also increases. Thus, the tendency to pull it down also increases. So, at the maximum velocity, when the car has the highest tendency to go up, the friction will also show its highest tendency, since it is static friction. So now, here the Fr should be made max to find the velocity v max. What is the value of Fr max? Fr max we have already discussed. That will be mu into n. Now just substitute here. Instead of Fr, I am going to substitute mu into n. Here also, instead of Fr, I will substitute mu into n, and here in place of v I will write v max. Now just we have to find v max from here. How we will find? Now let us write this equation like this. This is n cos theta minus mu n sin theta, that will be equal to mg. Now divide these equations. You will get, if we divide this equation by this equation, what you will get? This is, let us say this is equation number 1, this is equation number 2, this is equation number 3. Now let us divide these equations. This will be giving, n will take common from both the equations and it will cancel out. This will give sin theta plus mu cos theta divided by cos theta minus mu sin theta, that will be equal to, m will cancel m, and that will be equal to v square by rg. V square by rg. Now it is simple. Now just I will erase this part because this is over actually. So we will calculate the final v max actually. This is the v max. Okay. So now from here write v max as, v max can be written as under root of rg, that is sin theta plus mu cos theta divided by cos theta minus mu sin theta. Okay. Now if you have basic knowledge of trigonometry, this equation can also be transformed into a more simpler equation. What I am going to do, see very carefully, that divide in the numerator and denominator by cos theta, that will give me rg tan theta plus mu divided by 1 minus mu tan theta. So basically this is the maximum velocity that which we can attain while we drive the car, our car on the banked road at a speed greater than rg tan theta. Now in the next case we will be discussing the minimum velocity, when the velocity of the car will be going less than this. So note down this one, then we will discuss the minimum velocity case.
Go.
So now let us discuss this case very quickly, that what if we drive this velocity less than rg tan theta? No, nothing will change, only this friction will start acting upward, because as the tendency of the car is going downwards, so the friction will act upward to oppose the tendency. Just write the equations similar to the above case, just change the direction of friction. So this will be n cos theta plus fr sin theta equal to mg, and n sin theta minus fr cos theta equal to mv square by r. Now here, to make the v minimum, again I have to make the fr max. Now this is the only thing that we need to learn here. See, the tendency is to go downwards. As the car goes downwards, this fr will increase to oppose, and fr will increase to maximum value at v minimum. So just put fr here mu into n, here also mu into n, and here this v will be minimum. Now if you calculate the v minimum from this expression similar to the previous case, then you will get the following expression again. V minimum will be under root of rg tan theta minus mu divided by 1 plus mu tan theta. So these were the three cases of the banked road and the horizontal circular road which we discussed. Thank you so much.